Okay, welcome to the lecture 20 of this classical mechanics 1, and let me remind you that in last lecture, lecture 19 and lecture 18, we were considering symmetries and conservation laws. We have seen the three different symmetries and three different conservation law. We have seen that if the system is invariant under space translation, then linear momentum of the system is conserved. If you have the time translation invariant, then the total energy is conserved, T will be cyclic. And lastly, we consider if your space is isotropic, when space is called isotropic, when it is rotational invariant. So, if you have a rotational invariance in the theory, then you will have angular momentum conservation. So, now we will consider in this lecture, we will continue with the symmetries and conservation laws. Particular emphasis on that examples. So, this symmetries and conservation laws we have studied. We will consider few examples to have a better understanding. So, let us consider example of rotational invariance. Okay. Let us consider this Lagrangian x, y, z in the Cartesian coordinates, which we will take as a generalized coordinate here, x dot, and let me write a specific Lagrangian x dot square plus y dot square plus z dot square minus half m omega square x square plus y square plus some constant times z square. Now, one can verify, you can verify yourself, this Lagrangian is invariant under rotation about z axis. Okay. So, let us consider a rotation about z axis, and we know if you have a rotation about z axis, then x y coordinates changes. So, let us for angle theta rotation, you can write cos theta sin theta minus sin theta cos theta. This is well known to you that under rotation about z axis, your the plane x y plane will change and x and y coordinate will be changed under this. So, this is rotation matrix. Okay. So, now if you write your Lagrangian, and also z will not, because you are making a rotation about z axis, so z will be same. So, if you now write this Lagrangian in terms of x prime, y prime and z prime, x dot prime, y dot prime and z dot prime, you will find, just do a simple algebraic calculation, you will find by substituting this and corresponding dot, you will find half m x dot square plus prime y dot prime square plus z dot prime square minus half m omega square x prime square y prime square plus c z prime square. So, one can check that this. I will tell you the how to know before verifying that this will be the invariant, this Lagrangian will be. So, this system has a rotational symmetry. That means the xy plane, it is isotropic in the xy plane. So, rotational symmetry, and this rotation is about z axis. But you can verify yourself this Lagrangian L is not invariant under rotation about x axis or y axis. You can verify yourself, you can write similar transformation for rotation like this. This is the rotation transformation for rotation about z axis. Similarly, you can write your when you have a rotation about x axis, yz plane will change. Similarly, when you have a rotation about y axis, xz plane will change, and you can write the transformation explicitly. Notice that under the rotation in z axis, x and y prime is changes in this fashion, sin theta cos theta sin theta minus sin theta cos theta in this matrix, and you can verify yourself that actually x prime square plus y prime square is basically x square plus y square. So, when you look at your Lagrangian, that this x square plus y square term has the same coefficient, immediately you can say that this term will be the invariant under rotation about z axis. Okay. So, immediately we can say that this Lagrangian is invariant under rotation about z axis. So, mz, that is the angular momentum z component will be conserved. Okay. So, this is an example, explicit example that you can verify yourself. If you are given Lagrangian, you are supposed to find that whether it is invariant under any rotation, and if you find one rotation, you can find corresponding to that there will be some component of angular momentum will be conserved. Okay. So, of course, I remind you here for symmetry you need not check the Lagrangian, only requirement is the action should be invariant, but if your Lagrangian is invariant, which is more constrained, more strict, is invariant, then of course action will be invariant. But even you can have some examples where Lagrangian changes by total derivative or Lagrangian changes trivially, then also you can have your action is invariant and will have the same symmetry and conservation laws. So, example 2. We consider a Lagrangian, which let me write half m r dot square plus r square theta dot square minus say v r, where this is v is only function of the magnitude of the position vector r. So, this kind of system is called the central force problem. And later we will see that for central force problem, where the potential or the force only depends on the magnitude of the position vector, then angular momentum is conserved for that system. So, here this two body central force problem we will learn later in this course. So, this system is rotational invariant. Invariant, and you can clearly see that theta, that coordinate theta is cyclic here. Theta is cyclic here, and you find that angular momentum which is also the momentum conjugate to theta is conserved. So, P theta will be del L del theta dot, which for this Lagrangian we can calculate that m r square theta dot, and one can show this is nothing but the angular momentum. So, later for two body central force problem we will come back to this, that central force problem angular momentum is conserved, and this is associated with the symmetry of the system. So, now let me recap here what we have done in symmetries and conservation laws. So, whenever we have a symmetry, there will be a conservation laws. And further, this will be related to cyclic coordinate. This we have learned, and we have checked for three different symmetries is space translation. Space translation symmetry is related to the homogeneity of space. Then we have seen time translation is the homogeneity in time. Then we have seen the rotational symmetry, which related to the isotropy of space, and we have seen the corresponding conserved quantities. Here I want to mention there is a theorem most generally taught in the quantum field theory, which says about the symmetries and conservation law, and that theory is known as Noether's theorem. So, Noether theorem says that for every continuous symmetry, I will have to define what is continuous symmetry, what is discrete symmetry. Symmetry, there will be conserved current, the charge corresponding to that conserved current will be the generator of that symmetry transformation, generator of that symmetry transformation, okay, and vice versa. So, I have to explain several technical terms: continuous symmetry, the conserved current, charge, generator of the symmetry transformation. So, these are new words, but we are not going to discuss or proof of Noether's theorem in details in this course. It is generally taught in a first course in quantum field theory, but you should have a overall idea of this. So let us define one by one. So, what is continuous symmetry? So, every symmetry or every transformation involves a parameter. If that parameter take continuous values, then we call it as continuous transformation. So, the depending on the transformation parameter, whether it can take continuous values or discrete values, we call as transformation is continuous transformation and or a discrete transformation. For example, the translation, when you have a space translation, R I prime is defined as R I plus A. So, this parameter can have continuous value. So, translation in space we can say is a continuous transformation. Similarly, when you have a translation in time, that also you can have a continuously change. So, this is also the rotation parameter, the rotation angle. So, in rotation, angle will be the parameter. In rotation, the angle will be the parameter. So, theta, the angle of rotation, will be the parameter. And it can have it can take continuous values. So, rotation is also a continuous transformation. So, what Noether's theorem says that whenever you have a continuous transformation, and if your theory is invariant, the action is invariant under this continuous transformation, then we can say that it has a continuous symmetry. Then there will be a conserved quantity, and these theorems call that conserved quantity as a conserved current. So, whatever conserved quantity will have, they are defined as a conserved current, and its zeroth component of this current is generally called charge. In electromagnetic theory, we know the charge is the zeroth component of the current. So, in something called 4 vector notation, so I am not going to that detail. So, some component of the current is called charge, and then this charge will generate that symmetry. So, this is the so Noether's theorem is much more involved. We are only in the first part, that if you have a continuous symmetry, there will be a conserved current. Okay. So, that we have checked for 3 continuous transformation, we have. Now, if you what is the transformation, we will have some example of discrete transformation. For example, space reflection. Is an example of discrete transformation. Similarly, parity, which is also parity, time reversal. These are the example of or charge conjugation. The example of discrete symmetry. So, in the discrete symmetry, you will have some consequence. Discrete symmetry, if your theory is invariant under certain discrete symmetry, then Noether's theorem is valid only for continuous symmetry, but even if you have your theory is invariant under some discrete transformation, then also you will have some consequence. Okay. So, this is discussion on conservation laws and symmetries. Now, we will consider further, one more very interesting symmetry or transformation which is related to the principle of mechanical similarity. So, next topic we will discuss is the principle of mechanical symmetry, which is associated with the scaling transformation. So, next we consider scaling transformation and principle of similarity. So, scaling transformation and principle of mechanical similarity will be next topic, and you will find that if your Lagrangian is invariant under certain scale transformation, then from that we can extract very rich physics or very rich information about the system. So, that we are going to learn, and this is known as principle of mechanical similarity. I refer this Landau-Lipschitz book for this topic, or there are many other books also. So, this principle of mechanical similarity we will understand how powerful that scaling transformation symmetry or scaling symmetry. So, let us consider a Lagrangian which is T minus u, and we assume that T, the kinetic term, is quadratic, is a homogeneous function of velocity of degree 2 or quadratic function of generalized velocity. And also we will assume this depends only on generalized coordinate, the potential energy u qi is a homogeneous function of generalized coordinate of degree k. So, k is some integer, can be positive or negative integer, and this we assume that we consider a system where the kinetic energy is a quadratic function of generalized velocity and the potential energy is a homogeneous function of the generalized coordinate of degree k, and we consider the following scaling. We scale all the coordinates r I prime to some number alpha times r I. So, all coordinates will scale in this way, and the time we scale with another number t. So, t prime equal to beta t, and alpha is the scaling of the coordinates. All coordinates with this scale by same amount, and time is scaled by a factor of beta. So, this is scaling transformation. Okay. So, under this transformation, how your t will change? So, naturally t prime will be alpha by beta whole square times t, because your v prime is actually dr dt. So, this will be alpha by beta times v, because t changes by beta factor, r changes by alpha factor. So, v will change by alpha beta, and since kinetic energy is a quadratic function of degree 2, it will be alpha by beta by t. What will be the how the under this scaling potential energy will transform? Potential energy will transform alpha to the power k times u, because it is a homogeneous function of degree k. Each q transform multiplied by a factor alpha. So, there will be k number of terms in the each terms in the u. So, all the terms will be proportional to the alpha to the power k. So, under this scaling, the kinetic energy and potential energy will transform like this. So, how your Lagrangian will transform? L prime is a t prime minus u prime. So, it will be alpha by beta whole square times t minus alpha to the power k times u. It is very simple. Now, recall we studied a properties that dynamics will be unaffected if two Lagrangian L prime and L are related by a overall constant C. So, C is constant. So, dynamics will not change, or we can consider that will be a symmetry if the Lagrangian is by that transformation is changes by a overall constant. So, now if we demand alpha beta are two arbitrary number. So, alpha beta two arbitrary number, but now I make a relation between alpha beta in such a way that alpha plus beta whole square is alpha to the power k. Then your Lagrangian L prime will be alpha by beta square times L. So, this is a constant. Okay. This I can express in other way. So, alpha by beta square by alpha k implies, this implies your beta equal to alpha to the power 2 minus k by 2. So, if I have a scaling that r prime is alpha times r and t prime is beta, beta I will replace alpha by 2 minus k by 2 times t, then we have a scaling symmetry in the theory. So, we have a scaling symmetry in the theory. Now instead of two independent parameters, we have only one parameter alpha, and we find the dynamics will not change. Lagrangian will shift by L prime equal to C times L, a overall constant. So, this is very interesting that this is a I can scale my coordinate and time this with the arbitrary parameter alpha, where coordinate transform alpha times the old new coordinate will be alpha times old coordinate, and new time t will be alpha to the power 2 minus k by 2 times t, where k is the degree of the homogeneity of the potential function. Now, this will give you very important information of the system. That we will learn in the next class, because the time is over for this class. So, we will continue with the principle of mechanical symmetry in the next class. So, we will find that how this is very important, or using this simple trick how we can extract very useful information about the system. So, we will continue from here in the next class, and then we will find different system, how these properties give a rich information about the system. Okay. So, let us continue this topic in the next class. Thank you.